If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Please share it with all others who might benefit. Let's get started. So one of the key topics in unsupervised learning that's known as principal component analysis, which is essentially used for dimensionality reduction, is considered to be a tricky topic. It is tricky because it becomes a little math heavy beyond a point. But what we'll try to do in this video is that we'll try to give you proper intuition behind principal component analysis so that you're able to understand why it is useful and how it is applied. What works behind principal component analysis is what you'll get a lot of clarity on. In the process, we'll discuss all the common terms so that you have a lot better clarity on everything to do with principal component analysis from an applied perspective. Let's get started. Before we deep dive into principal component analysis, it's essential that we understand the concept of correlation. So what is a correlation? A correlation generally captures the degree and direction of association of two variables. In our example right now, you see a variable y on the y-axis and a variable x1 on the x-axis. So what we are saying is that as x1 increases, y also seems to be increasing. This is an example of a positive correlation. On the other hand, if x1 increases and y decreases, you will see a negative correlation because it captures the degree as well as direction. The degree is something that you measure by looking at the proximity of these points in the two-dimensional space. The farther these points are from each other, the lower would be the degree of association. The closer or more tighter these are bound would be a higher degree of association. So generally, this may be relevant when we are trying to, let's say, predict a value of y using an independent feature x1. We'll take some examples on this as we progress. So in general, when we talk about predictions, this kind of relationship is considered good between a response or dependent variable and a factor or an explanatory feature or an independent variable. But we do not want the independent variables to be correlated to each other. Imagine your task is to explain y using x1 and x2. But here what's happening is that x1 and x2 themselves are correlated. This could lead to problems. So we'll be good if we are able to explain the target or the outcome with the help of independent features. But we do not appreciate the independent features being correlated. Why is that so? Let's understand next. So let's say your task is to explain the duration of employment in months, let's say for an employee, and you're trying to look at the annual salary as one of the explanatory features. Now you can imagine if a person is satisfied with the salary, the employee might continue to work for a relatively longer duration. That's our guess. We don't know that's guaranteed or not, but we are trying to guess that. This is just one variable, annual salary, trying to explain the duration of employment in months. This is the case of y and an x1. So y is being explained with the help of x1. Let's say we have been given the freedom to pick another variable. Apart from annual salary, you've been given a couple of choices to choose another explanatory feature or independent feature. Now here are your choices. Would you choose monthly salary or would you choose one of these, let's say prior experience or education or performance rating or employee satisfaction score? Employee might have rated the organization. Which of the two choices, A or B, would you like to go with? You have to choose one of these only, and within B also you have just one of the choices. I hope you get an idea that monthly salary and annual salary could be connected to begin with. So for example, typically monthly salary multiplied by 12 plus minus the adjustments for taxes and allowances would lead to the annual CDC or annual salary of an employee. So using monthly salary as another variable would not add explanatory power to your model because monthly salary and annual salary are likely to be correlated. On the other hand, the features like prior experience, education, performance rating, employee satisfaction would bring some amount of freshness. You'd not be using redundant variables to explain the same outcome. Now, it so happens that generally when we capture data, the variables tend to be correlated. For example, let's say while trying to explain an outcome, you capture fields like age, experience, and salary. Now, there is a possibility that experience and age are correlated because experience would be a subset of age only. Certain years of experience would come from a certain age. And as the person's experience grows, the salary is also likely to grow, performing a particular job role. So there is a natural tendency for the variables to be correlated. Now we understand the variables as we collect them might be correlated. If we keep on adding such redundant variables, it would not help us improve our model's performance. Therefore, there has to be a way using which we are able to treat this correlation property of independent variables, which is also known as multicollinearity. So remember, we are okay to have correlation between a dependent variable and independent variables, but we are not okay for independent variables to be correlated themselves. And principal component analysis is one such technique that helps us eliminate multicollinearity in our data. So now let's understand PCA as a dimension reduction technique. A lot of people believe that PCA is dimension reduction. So let's say if you have three features to begin with, let's say x1, x2, and x3, PCA must be dropping one of these features. Let's say drop the feature x3, we'll be left with x1 and x2. It drops the feature x1, we'll be left with x2 and x3. Or it drops maybe x2, we'll be left with x3 and x1. But PCA doesn't drop the original features. Instead, what PCA does is something like this. PCA transforms the original data into a new data. PCA is a transformation on the original data that comes up with principal components as the new features. So you had these three variables, x1, x2, and x3, and you can see each PC has some portion of x1, x2, and x3. So you've not dropped any of the original features. You've attained a transformation on the data, wherein each principal component assigns a certain weight to the original features. And this assignment might vary from PC to PC. End of the day, no two PCs will be identical. Let's look at the mathematical part of it. So let's say this is the transformed data. How are we going to give weightage to the original features? So each PC is a linear combination of the original features. We have PC1 written as A1x1 plus A2x2 plus A3x3. What are these A1, A2, A3 values? These represent the impression or importance of each variable onto a principal component. We will be getting this using something that's known as the eigenvectors. We'll be talking about that soon. Similarly, PC2 can be written as a linear combination of the original features x1, x2, x3 and these coefficients. Again, these coefficients b1, b2, b3 would represent how important these variables x1, x2, and x3 respectively are for PC2. So is the case with PC3. This has different coefficients C1, C2, and C3. And the number of principal components that we extract will be same. So if we start with 200 variables, the PCs that we extract are 200. Then the question comes, how does the dimension reduction take place? Let's understand this with the help of an analogy. Let's say we have a tennis ball and you are made to sit at the center of this ball. Now you have to make it to the surface and you're told that the distance that you travel from the center to the surface will be rewarded. Would you have a preferred direction in which you'd want to move? The answer is it would not really matter because this ball is spherical in nature. So you go in any direction, you have to travel the distance that's equal to the radius of this tennis ball. There is no particular direction where you'll be able to maximize your reward. All you have to do is start from the center and make it to the surface. You can't go zigzag. You have to go straight only. Now you go in any direction, it's going to be one and the same reward for you. But if the scenario was a little different, for example, if you had this rugby ball, now you see this is not symmetric. If you were to be rewarded for making it to the surface from the center, you would probably be choosing this direction now. Why? Because this captures a larger spread. This is exactly what principal components follow. They try to capture the variation in the system, and these PCs essentially are extracted in the order of importance that's given as per the amount of variability that they capture. So PC1 in this case, you can imagine, captures the larger spread. That becomes most important. The next PC cannot be at any other angle to this other than 90 degrees. Why? Because the whole idea was that you want to eliminate correlations. When you have features which are correlated, you would often find they're aligned at a certain angle other than 90 degrees. But in this particular case, you can see that PC2 is orthogonal to PC1, which means PC1 and PC2 are independent. So all the PCs are extracted keeping this basic logic in mind. They have to be orthogonal to each other and they're extracted in the descending order of the variability that they capture. Now you can imagine this shape actually resembles the correlated variables. If you have two variables which are correlated x and y axis, you can imagine this is how the shape you get. But when your data is more spherical in nature, it will be all over the place. There's no specific direction that you can say it's more important for us to measure that. Whereas in this case, you clearly have a direction that's relatively more important compared to the other directions. So now coming to some terminology. Eigenvectors represent the direction in which PCs are aligned. That's the importance of eigenvectors. Eigenvectors are the vectors that provide us those coefficients of the principal components that we just talked about some time back. Now there's another term called eigenvalue, and let's understand this with the help of another analogy. So let's say there are four friends who want to become business partners. They have a business idea and they want to start the business in partnership. They estimate the initial capital required is $4 million. Now, if they want to put equal effort and want to claim equal rights on the business, I think you can imagine how much each partner should contribute. It'll be 4 million divided by 4. That'll be 1 million each. That's what initially is agreed upon. But at the time when they had to actually bring money, one of the partners actually brings more money, that's 1.8 million. The second partner brings 1.2 million. The remaining two partners are not able to, for whatever reason, contribute what was initially agreed upon. So the third one here only contributes 0.6 million and the last one only contributes 0.4 million. They are still able to make it up to 4 million in total, but you can see some of them have contributed more and some of them have contributed less. So let's look at the proportion of contribution from each of these. The total contribution is 4 and we have these as the shares. So we'll divide it by the total and we'll get this number. If we convert it to percentage, this is how it would look like. So the first partner has contributed 45%, second one has contributed 30%, the third partner has contributed only 15%, and the last partner has contributed 10%. Had this all been equal, 1 million each, everybody would have contributed 25%, 1 divided by 4. Now, if you look at it cumulatively, first partner has contributed 45. First two partners have contributed 75, and first three partners, if you look at, have together contributed 90%. Shouldn't this be the way we should look at the rights to be assigned to these people on the business? Shouldn't the person who has contributed more be given higher value and importance? The answer is yes. And this exact is the same logic that works in case of principal components. So we discussed number of principal components that can be extracted will be the same as the number of original features. But there must be a way that we are able to reduce the principal components. And that's done using a similar logic. That's through the eigenvalues. So eigenvalue essentially represents the variance or spread captured by each principal component. In our analogy example that we were giving, it was the amount contributed. In case of principal components, it's the eigenvalues. So those who contribute more should be given higher importance. First of all, the principal components are always extracted in the descending order of these eigenvalues. Just like in our case, we looked at the first partner who contributed the most and the second highest and the third highest. This is how the PCs are extracted. And higher the eigenvalue, higher the relative importance of a PC. Just like in our example, the partners contributing more to the business would be given higher importance. So what does it help us achieve? It helps us separate the vital few from the trivial many. The example we took was a toy example. Just to illustrate, we took an example of 4 partners. But in real world, this could be 40 features, which you can cut down to maybe 5 or 6 important features, which are vital few, compared to the 40 overall features, which were trivial many. When we are conducting principal component analysis, we derive the coefficients for each principal component. These coefficients signify the contribution of the original variable to the respective PCs, and their magnitudes indicate the strength of this influence. Remember that equation PC1 is equal to A1x1 plus A2x2 plus A3x3? That's what we are talking about here. So once the PCs are extracted, we can look at the relative importance that those PCs assign to these features, the original features in our data. Let's look at it with the help of another example. Let's say we have some data, we have some lab tests that have been done for certain patients. We've captured their bad cholesterol, we've captured their hypertension readings and the blood sugar levels. And we have a lot of data for a number of patients. Let's say we found by analyzing the data that first 2 PCs alone add up to 90% of the cumulative explained variance. Now, what is this cumulative explained variance? This will be the sum total of the eigenvalues of PC1 and PC2 divided by the total that will be same as the number of features that we had in our data. So let's say first 2 PCs alone add up to 90%, just as in our case, first 3 partners added up to 90% contribution. That's how we are looking at this. And let's say when we perform principal component analysis using a tool, we are able to extract the eigenvectors, which brings us the coefficients. We talked about an equation which was like this: A1x1 plus A2x2 plus A3x3. A1 here is 0.9, A2 is 0.75, and A3 is negative 0.25. Likewise, PC2 has B1 as 0.1, B2 as 0.06, and B3 as 0.93. Now, how this is extracted is a mathematical portion. You'd almost never be doing it manually. You can rest assured. It'll be done with the help of a proper library, a tool. Once we extract these, let's see how the data is transformed. So now, let's just take the first row. Can we derive a value of PC1 using this equation and these original values? And similarly, can we take this row and derive the value of PC2 using these original values? We just have to plug the coefficients and the values here. So it would appear like this. So for PC1, it's 0.9, that's the coefficient, multiplied by the first value in the reading, that's 169, you'll get that. Then coefficient 2 and the second value. So the coefficient 2 is 0.75 and the second value is 185. You can put it here, so on and so forth. You can do the calculation. So once you do the calculation, you'll get the value of PC1 corresponding to this row as 255.10 and the value of PC2 corresponding to the first row as 160.99. You would do this for every single row. That's how the dedicated functions in the libraries work. And if you do that, you'll be able to eventually obtain a transform data. We just showed you for one row, but you can imagine if you take the second row and apply the same coefficients, a1x1 plus a2x2 plus a3x3, you'll get values like these. Now, this was the original data, and this is the transform data. So what have we achieved? If there was a correlation between the original features, let's say LDL, hypertension, and glucose, you can rest assured these PCs that you've obtained now will have no correlation. We'll demonstrate this when we do the hands-on exercise. We'll take a proper data with multiple columns, which would have traces of correlations. And when we extract PCs, we'll see that principal components do not exhibit any form of correlation. Now let's move on to the prerequisites of principal component analysis. First of all, this is meaningful only if the independent features have correlations. If the features to begin with do not show correlations, there's no point applying principal component analysis. Second is the kind of correlation that we are talking about here is meaningful only for continuous numeric variables. PCA is a concept that's applied to numeric data. You should not be applying PCA to the categorical variables. That's not how it's supposed to work. Third is your data should be free from outliers. Now, if you check the formula for correlation, you'd realize that uses averages and standard deviations. So if there's anything that uses average, you know it gets affected adversely in the presence of outliers. So your data should be free from outliers when you're doing PCA. And preferably, the variables that you're dealing with should be on comparable scales. This becomes very important for specific libraries that the data needs to be scaled before you perform PCA, unless your data is pre-scaled to begin with. So that's pretty much about the principal component analysis, the theoretical aspects. You'll see more of it in action when we do the hands-on exercise.